Hello everyone, my name is Sarah Chong and I'm a rising senior majoring in biophysical chemistry at Dartmouth. This summer, my mentor, Dr. Michael R. James, and I are working to update the gamma spectroscopy libraries and analyze the effects it will have in simple data processing and analysis. To start off, some background about the count room. We are under the chemistry division and part of the nuclear and radiochemistry group. We were founded under the support of the U.S. Nuclear Testing Program. Today, we support numerous programs such as bioassay, treaty monitoring, and nuclear forensics. We perform qualitative and quantitative assays of gamma, beta, and alpha-emitting radionuclides in a variety of matrices and over a wide range of activity levels. Annually, we make around 55,000 measurements, and other goals include making database-backed web visualization tools as part of the team's consistent efforts to modernize and develop new instruments and methods of development. Continuing to the topics of my summer project, libraries are important because it is a database of gamma spectroscopy information used by the analysis codes to process experimental data. The data we are editing originated in the 1970s, and various ad hoc updates have been made over the years. However, historically, priority has been given to continuity instead of modernization. Since the nuclear data has been constantly updated and improved over the years, we have decided to do a complete update to the gamma libraries using data from the NUDAT database maintained by the National Nuclear Data Center. And here we have the mathematical definitions of radionuclear activity, later referred to as disintegrations per minute at zero time, dpm at zt, and radioactive decay equation. The peak energy and area comes from the analysis, and this peak energy is matched to the library to determine the isotope. The probability of emission and half-life are also from the library, while the efficiency is from the detector calibration. The libraries are made up of two parts. The first part shows a list of around 80 isotopes in order of increasing mass, a section of which is shown here. The first column is isotope cadmium 109 to antimony 125. The next two columns are its mother-daughter relations, if there are any, then the half-life in days and primary peaks in keV. Shown here is the before and after with edits colored red. As you can see, the magnitude of the changes are usually not big. The second portion of the library file is a list of the same isotopes as in the first part, but listing the most important peaks and their probability of emission. This portion can be a couple hundred data points. Again, as you can see, the magnitude of changes are usually not big. Once the libraries have been edited and double-checked, a SpecNL analysis code is run using the data from a calibration solution containing multiple isotopes in a 5 ml solution. Then, the data was collected using counter 172 for 41.9 hours, about 10 centimeters from the detector face. Shown here is a gamma spectrum showing the prominent lines from each of the isotopes in the solution. The SpecNL code identifies peaks and quantifies the isotopes, using the library as its database. This test was run twice, once with the old library data and then with the new library data. These example lines from the SpecNL output showing two of the identified isotopes, potassium and cobalt. From the output of the analysis code, we want to pay attention to the activity expressed in decays per minute at the zero time, which is the activity at count time decay, corrected back to a reference time. Here I have calculated the percentage difference in the activity. The first column shows the type of isotope, followed by comparisons of the activity, and then the magnitude of the changes. Although the number changes are normally insignificant, further analysis shows that the percentage difference can be quite significant, as shown here with the red arrows. These cases will be further analyzed. This work shows the results from the changes and testing of the first library. Currently, we have finished updating and started testing the next two libraries, and the goal is to finish updating and analyzing all 9. Since each library serves a different function, we will need to run different tests for each one. Finally, since our detectors have been calibrated with the old libraries, we will investigate the impacts of the changes in the library values will have on the calibrations. Thank you everyone for listening, and a special shout out to my mentor, Dr. Michael R. James, for being patient and teaching me remotely. We would also like to thank the support of the AFTAC Nuclear Debris and Analysis Program.